Good morning, everybody. How y'all doing? Welcome to another installment of chemistry knowledge and learning from your old pal Stu. So we are done with acids and bases. We've learned everything that we need to know. We got H, we got OH, Arrhenius, Bronsted, Lowry, neutralization, titrations, blah blah blah, acid, base, mix, water, and salt, all that kind of good stuff. So what we're going to do now is we're going to dive into one of the last few chapters of the year. We're going to learn about this special kind of reactions called redox reactions, and the whole reason we're going to look at this chapter is because it is the science behind batteries, like how batteries work, how we store energy, like how is it that we can get this little thing for like chemicals, how does electricity come out of it? Kind of a big deal right now. I mean, look around, just about everything that we own works on batteries. And hopefully, if we can get our heads in gear, we will be moving away from fossil fuels, so we can try to not, kill ourselves or your generation with, destroying the world we live in, and hopefully move to something like a battery, which, if we can do it right, maybe won't. Who knows? The only future can tell. So the whole point of this whole chapter is to learn about how batteries work and the chemistry behind them. So you guys ready to dig in? Because you know what? I most certainly am ready to dig right in. So there we are. Chapter 9. These kind of reactions are called oxidation and reduction reactions. You see what I'm saying right there? It's an oxidation and a reduction, and it is often referred to as this, as, wait, let me get this thing going here. It is called a redox because it's like a mishmash of both oxidation and reduction, mashed up into like a single word. So redox, both oxidation and reduction. And so before we really define it, I want to show you an example of what an oxidation and reduction reaction is, and then you may see. But what's important here, what I really need to look at, is what happens to the electrons, because after all, this is about electricity and what's happening to electrons in this particular kind of chemical reaction that makes your cell phones turn on, makes cars go, makes our computers work, all that kind of good stuff. All right, so here is a chemical reaction where we're going to start here with sodium and chlorine. Now, if you remember, sodium, solid, is a metal. It's shiny, it's silvery, it's beautiful. But if you recall, if you eat sodium, it will explode inside of you. It literally is an explosive metal. And here we have chlorine gas. And I don't know if you remember talking about chlorine gas. It's one of the nastiest things out there. You get to inhale it once. And it's what we call incompatible with life. However, when you put these two things together, you end up with this wonderful stuff, which is sodium chloride. Table salt, can't live without it. So if you ate pure sodium, it might be your last meal. If you breathed chlorine gas, it's going to be your last breath. But once they react, they create sodium chloride, vital for life. So what happens here? What is going on? How do we go from an explosive deadly metal and a deadly, unbelievably toxic gas to something that is absolutely vital for us to sustain our lives? Well, here it is. This is what happens, right? I'm going to go with golden here. If you look, this is what is referred to as uncombined sodium. It is a pure element, and here we have right here a charge of 0. In other words, it hasn't gained or lost any electrons. And here we have chlorine, just one. I'm not looking at the molecule, because each individual chlorine atom has a charge of 0, which tells us it has not gained or lost any electrons. However, once we have the magic of a chemical reaction happen, we end up with chlorine having a charge of +1. Which means that one electron went flying out of sodium. And if you look at your chlorine, it's got a charge of -1, which means that one negatively charged electron went into there. So what happened is chlorine took an electron away from sodium. The electrons went out of sodium and into chlorine. The electrons moved, and that is what is clutch for this redox sort of approach to chemistry. Electrons are moving, and dude, correct me if I'm wrong, but that is what electricity is. You get what I'm saying? So now, if you can figure a way to get like sodium over here and chlorine over there and like put a wire in between, you can have electricity. It doesn't really work with this particular reaction because it's sodium and chlorine, both deadly and super crazy reactive, and you don't really want to walk around with chlorine in your back pocket. But this is a great example of a redox reaction and how profound the changes can be, where you start with an explosive deadly metal and a crazy toxic gas, and you end up with these completely different ions. Why? Because electrons were being shuffled. You get it? It's all about the electrons here, right? The electrons are moving. That's the basic idea of a redox reaction. You guys follow me there? So, what happens when something burns? Well, let's look at burning magnesium. Magnesium is metal. Look it up on Google. It burns, man. It's so intensely awesome to watch magnesium burn. And here's what happens. We start with magnesium metal. And if you look, and if we write it down, it's just pure metal, right? It's a pure element. There's no compound. It hasn't combined with anything. Oh, and oxygen. High quality O2. If you look, oxygen has not combined with anything. So it has a charge also of 0. And so I'm showing you this one in particular because this is sort of where this word oxidation came from, because they looked at it way back in the day, all the sciencey people. They're like, what is this burning thing that happens? It's flames and bright and awesomeness. And of course they want to dig their little brain in to see what's going on there. Well, what's actually going on is that magnesium starts with a charge of 0, and if you look, it ends with a charge of +2. And each individual oxygen starts with a charge of 0 and ends with a charge of -2. So what happens when things burn? Oxygen is taking things away. It's taking electrons away from whatever it's burning. Does that make sense? The same thing with firewood or paper. Or you guys want to burn. If you're burning it, oxygen is taking electrons away from it. That's it. That's all there is to it. That's exactly what's happening inside our body. We breathe in oxygen. That oxygen then takes electrons away from something, and you have a redox reaction, giving off a ton of energy, which we then use to be alive and stuff. It's kind of fascinating, actually. It's called electron transport chain. You're gonna learn it when you get out of here someday. So that's what happens when stuff burns. Like, oxygen is taking electrons away. Now, it's really hard to take a burning piece of firewood and get electricity out of it. So this is not where batteries and electricity are going to happen, but it's the same exact process, right? So we got to start, and this is where it all started from, which is why we call it oxidation, because the whole digging into this started with people watching stuff burn and being like, dude, what is going on? And they're like, it's oxygen doing stuff. Let's call this process oxidation. Let's do that. So that's kind of where that whole thing started, and there's going to be some unfortunate, it is what it is. So that's kind of where, historically, where everything started. So, words, definitions. Let's go with Viking Red, because why not? Oxidation, reduction, reaction. Remember, this is also called redox. Totally interchangeable, like Robert and Bob, whatever. So the oxidation, reduction, reaction, redox is basically one in which it's a reaction in which electrons are transferred. This is super duper important. Electrons are transferred. That's it. Just the main core of a redox. And here, I'm going to scroll up for a second. The way that we can tell is the charge, right? This charge, or like the oxidation number, whichever way I want to call it, these things changed. Lock that in for later on. Okay. So, coming right back to this, here's something that I'm going to point out that seems sort of works like this. If I give you $5, that means I lose $5 and you gain $5. That's how it goes, right? I can't give you $5 and suddenly you got $3. It doesn't work like that, because that's stupid. That's right. If I had 3 rocks and I gave you 3 rocks, you would gain 3 rocks, I would lose 3 rocks. It's 3, right? The amount that I give you is the amount that you get. That's right. So silly to point that out, but I want you to lock in on that, because it's basically law of conservation of both mass and charge, right? Because it's electrons. Electrons have mass. Electrons have charge. So the amount of mass that you start with and the amount of charge that you start with is exactly the same as the amount of mass and charge that you end with, so that we can keep track of stuff. Balanced. Remember balancing equations? It's kind of like that, only it's charge and stuff. Easy, don't worry about it. You'll get it. All right. Two things that we need to get are oxidation and reduction. So oxidation. Oxidation is when an atom loses electrons. I don't know if did I spell that right? It's when it loses electrons, right? Because it's mixing with oxygen and it loses electrons, so we call it oxidation. And reduction, right? Reduction is when an atom gains electrons. Now, why would we call it like reduction if you're gaining electrons? Because this happened before we knew what electrons were. Like, you guys are in the 21st century. I'm your chem teacher. I have taught you about electrons. They didn't know about this back then, but I want you to dial into this. Let's come back up here to the examples. Reduction. In this case, oxygen is going to get reduced. And I want you to look at the charge. The charge goes from 0 to -2. The charge is being reduced. So that's what we're talking about. That's why we call it reduction, because the charge got dropped. Got it? Awesome. Not drop, but lowered. Oh, yes. How are we supposed to remember that? How? How could you remember that, like, reduction is when you're gaining electrons, and oxidation is when you... I have a thing. I'm gonna need you to, like, leave some space. I need you to draw along. How could you ever remember? So I'm going to draw. You follow along. Don't ask questions. Just draw. Just do what I do on your paper, and don't ask questions until the end. And don't fast forward, because you'll learn. All right, follow with me, right? First, we're going to go meow, 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 triangle of knowledge. Let's see, what else are we going to do? See what I'm drawing yet? I'm a bad jar, but you know, work with me. All right, now you got to get some squirrely, fuzzy hair. Is he a sheep? No, he's not a sheep. No, he's not a sheep. He's fierce. It's very fierce. This guy's very fierce. He's very fierce. Very fierce. Very, very dangerous. Whiskers. He's got whiskers. Oh, and he's got a paw. Yeah, you see the paw? And then we're gonna go like backwards number 2. Forwards number 2. And he's gonna have some girth. He's kind of a fatty. That's alright. So we still love him. And of course you gotta have the tail. There's your tail. And if it's a tail, you gotta go like that, because, you know, it's a tail. There. What does that look like to you guys? It's a lion. It's a lion. Of course it is. Now, what does this have to do with redox? I'll help you out. First of all, we're going to name this lion. What could you possibly name a lion? What is the most generic, stupid word you could ever come up with for a lion? Yeah, you guessed it. Leo. Now, what does Leo say? What's your lion say? No, they don't say roar, you silly pants. Leo, because he's like from Northeast Philly, he goes grr. Leo says grr. G-E-R. R. Leo says grr. Now, how is that going to help you with, redox? Watch. Lose electrons? Oxidation. Get it? It's so clever. Leo. It's like Leo. Lose electrons is oxidation. I don't even know if that's how you spell lose, but work with me. Is that... Wait, is that... I don't know. You know what I'm doing. Okay, well, over here, here's his name. Gain electrons is reduction. And now you have 2 of the 5 pillars of knowledge for this chapter. Leo says losing electrons is oxidation, gaining electrons is reduction. You got to remember that. You got to lock it in. And look at this beautiful bit of like this should be that's magnificent. I mean, I want you to send in the picture. I can't wait to see your notes to see how beautiful it is. Because that is a beautiful lion. That's art. It's art and it's knowledge all at the same time. You guys can thank me later. So here's the deal. If a redox reaction is where electrons are transferred from one electron to another. One thing, like losing electrons is oxidation, gaining electrons is reduction. It seems like we're going to have to find some way to keep track of where these electrons are and who's gaining and who's losing and how many. Why? Because when we make a battery, you know how a battery has to be placed in the right way, like it has to be positive this way, negative that way, or it doesn't work. That's why, because you've got to make sure we know which way the electrons are going. Also, you got to make sure you have either enough electrons or not too many. For example, if you took a car battery and plugged that into your phone, you're not having a phone anymore. That's pretty much that. But if your cell phone is trying to work off of like a hearing aid battery, that also might not be enough electrons to make it work. So why do we want to keep track of electrons? So that we know where they're going and how many are going to wherever it is they're going. So we can make a battery that actually works. You dig what I'm saying? So to do that, we got this. The oxidation number. The oxidation number, dude, it's just bookkeeping. This is the number of electrons gained or lost by an atom. That's all you need to know about this, okay? I'll go like that because you will need to know that number, that word. And it's literally like a bank account, right? You're gaining or you're losing. That's all there is to it. Here's an example. It's another chemical reaction where we have potassium and bromine. It's just like sodium and chlorine. They're like, this is group 1, this is group 17, so they do the exact same thing. This goes from a 0 over to a +1. This also goes, it's 0 because there's nothing there. It goes from a 0 to a -1. You guys get what I'm saying? So what this is telling us is that potassium lost an electron, so its oxidation number becomes +1. So oxidation number and charge are almost the same thing. They're kind of like identical twins. They look the same. They often act the same. It's kind of hard to tell them apart, but they are different. For us, it's going to be almost. It's really not going to matter for this level of chemistry. So yeah, the number of electrons gained or lost. And bromine gained electrons. Right? It went from 0 to a -1, so its oxidation number becomes -1 because it gained an electron. Does that make sense? So because it gained an electron, electrons are negative, right? So it's adding 1 electron. Remember, electrons are negative, so its charge becomes more negative. It's being reduced. Yeah? This potassium, it lost an electron. It's losing electrons. Leo says good. So this is being oxidized, right? So potassium is oxidized because it goes from 0 to +1, and the only way you can become more positive is to scrape off some of the electrons that are all negative. You guys get what I'm saying? And the other thing, the opposite thing that's happening, is that bromine is being reduced. It's going from 0 to -1. Gaining electrons is reduction. Now to keep in mind, remember what I said before about like if I gave you $5, I lose $5, you gain $5. If you have oxidation, you have reduction. If you have reduction, you have oxidation. You can't have one without the other. So if you can't remember which is oxidized, which is reduced, I always recommend look at the charges, look at the oxidation numbers. And whatever is going down, whatever is being reduced, whatever is being made more negative or lower on, or what is it, to the left on the number line or whatever, that's your reduction. Whatever charge or oxidation number is being lowered, that process is reduction. The other thing is oxidation. Does that make sense? Well, I certainly hope so, because we're going to move on to this thing, which I'm not going to lie. I'm throwing this out there because it's part of the curriculum, and there is no way on God's earth I'm going to be able to hold you accountable for this. You see that? So technically speaking, oxidation has the sign, the positive or negative first, and the charge has its second, like on the right. So the world, me keeping track of what's on the left or on the right, whether it's this way or that way, dude, I can't even write number 3s properly. So I don't really care. I just want you to know that sometimes you'll read something where it says the oxidation number is +1, but the charge is 1 plus. The reason they do that is to make us they need to have some way to delineate between oxidation number and charge. It becomes important later on when you dive deeper into chemistry, but for us, like I said, doesn't matter. I won't hold you accountable. Just want you to be aware of it when you see it. So, oxidation number, it's important. There must be some rules to keep track of it, huh? Oh, you bet your sweet bippy there are rules. There's 10 of them, and we're going to keep track of all 10. And dude, they're so easy. I have 10 rules here, and I want, as I go through these, for you to just chill. Remember, oxidation number and charge are almost the same thing, and you guys have been looking at and trying to figure out charge the whole year, right? So, bear with me. It's not as bad as it seems. So first thing we need is, we need your reference table, because there's a lot to remember here. So we need the good old periodic table of the elements, and we need table S. These two things are going to help us out immensely. I tend to look at the periodic table of the elements more often. I find that has way more information than I'm ever going to need. Table S is definitely helpful, but, you know, periodic table is where it's at. So let's get to it. Rule number 1. Let's go back to Viking Red. The oxidation number for uncombined elements is 0. Well, that's just like charge. If hydrogen is in elements, it's not in a compound, its oxidation number is 0. Excuse me, man. I'm inhaling dust here. I don't know what's going on. So, iodine, this guy. It is an element. It is not in a compound. That means its oxidation number is going to be 0. Oxygen, it's not in a compound. It's 0. Copper, it's by itself. It's 0. Magnesium, it's by... You guys get what I'm saying? This word is what tends to throw people off. Uncombined elements. All this word right here is saying is it is not in a compound. Got it? That's all that means. And just like the charge, if it's 0, the oxidation number is 0. All right. Same thing, only just in a different context. The sum of the oxidation numbers in a neutral compound is 0, just like charge. And this is really helpful for us to figure things out that we don't know. So sodium is always going to be a +1. How do I know that? I went to the periodic table of the elements. So then we got chlorine. Chlorine's here on the right, which means it's negative. So I go to the periodic table and I look and see what could it possibly be. Chlorine only has one option. It has to be -1. Has to be. Why? Well, because that's the only option. And these two things, the charges or oxidation numbers, have to add up to 0. You dig what I'm saying? Same thing here. Calcium. Calcium, let's pretend we don't know what it is. I didn't look it up, but I know that bromine is always going to be a -1 because it's on the minus side. And it only has one charge. So calcium has to be a +2 because there's 2 bromines, each having a -1. So -1 and -1, that's -2. Calcium has to be +2 because these all have to add up to 0 if it's a compound. You guys get what I'm saying? Hope so. It's just like charge. It works just like charge. The next thing... Oh, let's go back to there, sorry. The next thing I want to look at is the oxidation number for monatomic ions. Monatomic. These are ions with one atom. Charge and oxidation number are the same. So far, this is stuff you guys already knew, right? But just instead of using the word charge, we're using the word oxidation number because they function for us almost exactly the same. So here's the thing. For this one that's a little bit weird, but really not. It works just like charge. The sum of the oxidation numbers for a polyatomic ion is equal to the charge of the ion, right? So look, if this is a +1, if this NH4 is a +1, we go, this is first, so it has to be, this is a bad example. So I'm just going to tell you, nitrogen is going to be a -3. Hydrogen is always going to be a +1 except for very few exceptions. So if you have 4 +1s, 1, 2, 3, 4, and a -3. You add them all up, you're going to get +1, which is exactly equal to the charge. Over here, we have sulfur, and we have 3 oxygens. Sulfur, in this case, is a +4, and oxygen is going to be a -2, -2, -2. How do we know that oxygen is a -2? Trust, I'll explain that in a minute. So they all add up, +4, -2, -2, -2 gives us a total of -2. Right? I mean, it's just like charge. Charge and oxidation number are exactly the same. Here's another one. Polyatomic ion, OH. We just looked at this one. The charge here is -1. Why? Because this oxygen has a charge of -2. The hydrogen has a charge of +1. You put +1 and -2 together, it equals -1. Yeah? Okay, moving on. Let's go to number 5. You know, I have this up here in the notes, and every year I look at it and think to myself, you know, it's probably doesn't really matter. It really won't. But it explains weird things like this nitrogen. Like, why is nitrogen negative even though it's there? It's because the ammonium is from organic chemistry, which doesn't follow exactly the right rules. But the reason why we knew nitrogen had to be negative is because of this. The oxidation number for the most electronegative atom in a molecule or polyatomic ion is equal to the charge, right? So we look up nitrogen, we look up hydrogen, and we see that nitrogen has an electronegativity of 3, hydrogen 2, so that means nitrogen wins. It's going to get all the electrons. And if you remember, nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. So if this nitrogen becomes an ion, it's going to have to add 1, 2, 3 new electrons, making this whole thing have a charge of -3. That's how we know that nitrogen is a -3. You guys get what I'm saying? It's more electronegative, so it's going to take all the electrons. Same thing over here with the silicon chloride. Silicon has an electronegativity of 1.9. Chlorine has an electronegativity of 3.2. That means chlorine wins. It's going to be the negative one. So chlorine, 1, 2, 3, 4, 5, 6, 7. How did I know the chlorine had 7 valence electrons? Because it was the one on the far right. Like 7 is the number on the far right of its electron configuration. It's also a halogen. 7 valence electrons. So how many electrons does chlorine need to add? It needs to add 1 electron to have its great octet rule. Chlorine will have a charge of -1. I always go through these and they seem way more complicated than they're going to be when you guys solve problems. It'll be a lot easier once we start digging into the homework, trust me. Group 1 will always have a charge of +1. Group 2 will always have a charge of +2. Now you can memorize number 6, or you can just go to your periodic table of the elements and just look up the charge there, or the oxidation number. Look up the oxidation number, and every single element in group 1 will only be +1. Every single element in group 2 will only ever be +2, because that's your only option. You dig? Awesome. So here, number 7 introduces the very first brand new idea with oxidation numbers and stuff. Everything else we've kind of covered with charges and how charges have to be balanced and add up to 0 for a compound and whatnot. But this, you know that fluorine is on the way upper right corner. So it is the most electronegative of all the elements in the entire universe, which means it always takes the electrons. So fluorine is always -1. How often? All of the times. That's just how it is. Like, fluorine will always be -1. That's it. Moving on. That's all there is for number 7. For number 8, oxygen is always -2. Now that's duh. Look at the periodic table. Oxygen is listed as -2, but there is an exception. This thing called the peroxide polyatomic ion. Now, if you look at your table of polyatomic ions, you'll see that O2 has a -2 charge. And the only time you're going to see this in this class is here. This is hydrogen peroxide. Nasty stuff. One of the few compounds that I'm actually afraid of. And why is that? Why is hydrogen peroxide so nasty? Well, it's because oxygen, in this case, each oxygen has a -1 charge, which is really unstable. Oxygen does not like doing that. It much prefers to be a -2. So when we pour hydrogen peroxide on a cut or something, what happens is each one of these peroxide ions bumps into a molecule and rips the electron off, destroying that molecule. And it does so molecule by molecule. So when we pour hydrogen peroxide on our cut, it disinfects it by basically acting like a nuclear bomb and destroying everything that it comes in contact with. Everything. That's why if you peroxide your hair too much, it like will basically fall out after a while. Like if you bleach your hair too much, it just falls out because the peroxide literally destroys your hair molecule by molecule. That's how it do. And so for us, that's all you really need to know. Hydrogen peroxide, this is the only time oxygen is going to be -1. Moving on. Oh, I guess there's only 9. So there's only 3 new things that are new and weird. Fluorine is always -1. There's that pesky hydrogen peroxide, where that's the only time oxygen is going to be a -1. And this one. Hydrogen's weird. Hydrogen is +1 unless it's with a metal, in which case it's -1. But look, we're going to find a way to make that a little bit easier. Look, here's how it do. On this side, this is always positive. And this side is always negative. Always. So that means if hydrogen is here, hydrogen is going to be positive. Now over here, calcium in this case, is the positive one. How do you know that? Because it's right here on the positive side, right? That means that this hydrogen in this case, if it's on the right, it has to be negative. How do you know? Dude, because it's on the right. And we learned that since, like, I don't know, second marking period. First positive, then negative. Always positive, then negative. Always positive, then negative. When? Always. Like all of the times. So it's just nice to know that hydrogen is a weird thing. It can be positive or negative. If it's here, it's positive. If it's on the right, she's going to be negative. And that's all there is to it. You got it? Excellent. Yeah, table S. This is where I need you to go, because table S is where you're going to find your electronegativity values. You're not expected to memorize them, but you're expected to just look them up, because that's what we do. Nobody memorizes stuff anymore. We just look stuff up because there's too much stuff to memorize. And what you need to know is that whoever has the highest electronegativity is probably going to be the one that's taking all the electrons and have a negative oxidation number. That's all. That's all. Oh, yeah. Okay, I'll leave it. Or let's just do this. Let's just end it. You want to end it? Yeah, let's end it. 2 things. Finding the oxidation state. For this one, I'm probably going to have to put up a separate video, walking you through 1 or 2 of them just to kind of help you out. You've already done this exact same process in the past when we had to find the Roman numerals for our metals. It's the exact same process. We're going to find the oxidation state. It's just like finding the charge. It's just that we're going to call it oxidation state, and there's going to be more than just metals here. And then chapter 9, homework number 1, that is going to be in your chapter 9 homework packet. It's labeled chapter 9 homework number 1. That's your multiple choice one. You know how this works. Get them done, post them up. By the time I put up the answer key, no more late work after that. I hope you guys have gotten some learning done here. And I want to go back up here for a minute. 9 new things. Really, all that's new here is this one right here. Fluorine is always -1. Boom. You got some weird things for oxygen. It's always -2 unless you see it like this in hydrogen peroxide. Then it's -1. And this one. Hydrogen can be positive. We know that when it's on the left, but it can also be negative. We know that when it's on the right. Man, that's it. That's all the knowledge I have for you for today. So, live long and prosper. May the odds ever be in your favor, however you want to do it. Let's get some chemistry learning done so we can get the final done and be exempted from the regents. Can you believe that? Hope you guys have a great day.